Hello. In the previous class we discussed about Stokes flow past a circular cylinder. So, now we move on to Stokes flow past a sphere. Okay. So, since the title of the course is transport of microparticles, so most of the microparticles are spherical. For example, if you talk about microorganisms or colloids, so they are spherical. So this is going to be very helpful for us. Okay. So, Stokes flow past a sphere. Again we are considering axisymmetry case, so that we can introduce a stream function. So, what we do, we assume axisymmetry and via equation of continuity we introduce the stream function. So, this already we have seen. So, the velocities are defined like this in terms of the stream function. So, make a note in terms of 3D stream function, it is typically known as a Stokes stream function. Okay. So, we have Stokes stream function. Now, we are going to use this to solve Stokes flow past a sphere. So, let us consider the problem is similar to cylinder problem. So, we are considering a far field velocity, uniform velocity along z direction, and flow is assumed to be axisymmetric, and we assume no slip on the boundary of the sphere. So, this is a rigid impermeable spherical. Okay. So, once we have to get the corresponding equation for stream function, that also we have discussed. So, you introduce stream function, and then we have a bilaplacian in terms of stream function, right. But in this case it will be slightly variant. So, we have to derive. Okay. So, the corresponding no slip condition is again q equal to 0, and this is a far field, we have u along z. Okay. And this is the definition of the stream function. Now, I have shown you two examples how to derive stream function corresponding to a given velocity. So, what are the examples that we have in 2D? We have discussed u bar is u I, then corresponding to this what is psi of x y. So, we have seen already this is u y, and similarly corresponding to this psi is psi of r theta. So, this also we have discussed. Okay. So, therefore, what we need is similarly using Stokes stream function. If u is u k, so then what will be psi r theta. So, I think since we have already discussed, this should be a good exercise for you. Okay. So, you can do it. So, once you do, you will get the corresponding stream function. Okay. So, this is a far field for us now in terms of stream function. Why we have to reduce? Because we are solving the problem in terms of stream function. Now, consider the r momentum equation and theta momentum equations, because we are talking about axisymmetry. Now, introduce stream function. The procedure is same. What did we do to get the corresponding governing equation? We have considered the component form, then we have eliminated pressure, and we have substituted the definition of the stream function and velocity. So, more or less a similar process we are following. So, in order to do that, we considered r momentum and theta momentum, and we have the stream function. So, we differentiate this with respect to theta, and this before we differentiate with r, first you multiply with r throughout. So, that this factor r is gone, then differentiate with r and subtract. Okay. So, if we do this, we get okay. Now, if you do typically using component form, the algebra is very complicated. Okay, because you have the Laplacian involved on the right hand side. So, that will give some challenges, right. So, maybe let us understand the problem first, assuming that we get this equation. So, then towards the end I give some hints on alternative approach how to derive this equation, and maybe more details you can do it as a exercise. Okay. So, for now what we are assuming from these momentum equations, by eliminating pressure and using this definition, we get E for psi 0. Remember, in polar coordinates or Cartesian we got del for psi 0. So, here we get E for psi 0, where we have the corresponding definition of E square. Okay. So, once we have this operator, we try to convert the problem in terms of stream function. Okay. So, this is a no slip, then far field we have. Look at the far field structure. Okay. So, the problem at hand is now solve E for psi equal to 0 such that psi goes like as r goes to infinity, then you have no slip. So, that is nothing but psi equals to 0, dou psi is 0 on r equals to a. So, this is the problem, it is reduced to this. Now, this is a partial differential operator. So, now psi is function of r and theta, and anybody who has done first course on PDE. So, they will be attempting for something like a function of r, function of theta. So, this is a separation of variable solution. Okay. But we need not do for a generic case here. So, the reason is, look at the far field behavior. The functional form of the far field behavior is r square times sin square theta. Okay. So, in particular the functional form of theta is sin square theta, which means any other functional form towards g do not contribute, because we have homogeneous boundary conditions. So, once you force, you will get a simple algebraic system. Corresponding coefficient of sin square theta will produce a non-trivial solution, and other than sin square theta, any functional form you have, we get a trivial solution. So, therefore, what we do is we seek trial solution of the form function of r times sin square theta. Again I am repeating, this is due to the structure of the stream function. Okay. So, therefore, we have E for psi 0, okay. E square is this and E square is this. So, E for psi 0 implies simplified form, okay, because this is valid for only this functional form. So, once you operate, okay, you get this. So, now it is a differential operator, and you will see one can get the solution very easily. It is a Euler-Cauchy type. So, therefore, one can get the solution very easily. So, once it is Euler-Cauchy type, what we do is typically we look for polynomial solutions as powers of r. Okay. So, that is what we do. We seek solution of the form f proportional to r power n. Okay. So, let us say you take f equals to some constant times r power n and substitute. So, then we find these are the powers which lead to non-trivial solution, okay, corresponding to n minus 1, 1, 2 and 4. So, therefore, our solution structure is a by r, b r, c r square, d r 4. Okay. So, this is the structure of the solution, and correspondingly now we have to take the far field condition and no slip conditions, and then determine the arbitrary coefficients. So, here once we have f of r is A by r, B r, C r square, d r 4, we have the corresponding psi as because our psi is nothing but f of r to sin square theta. Okay. So, now our condition is this should behave like u by 2 r square sin square theta as r goes to infinity. Okay. Or in terms of velocity, u bar should behave like u k, okay, as r goes to infinity. So, either of them can be used. So, let us see the psi notation. So, we have psi given by so this is psi we have, and we need r square sin square theta. Okay. So, this will be a over, so we are taking r square common, okay, plus c plus d r square. Now, we need this should go like u by 2 r square sin square theta as r goes to infinity. So, this will imply, so these going to r goes to infinity, these goes to 0, and we get, so this is more regular than r square. So, which we do not want at infinity, because at infinity the maximum regularity we have is r square. So, therefore, d is 0 and c must be u by 2. Okay. So, that is what we got here. Now, once we have this structure, remaining coefficients are we have a and b. Now, we have no slip, q r is 0, q theta 0. Either we can use in terms of the corresponding stream function, or in terms of velocity we can use, and then we get the corresponding algebraic equations which determine a and b like this. Okay. So, I am not giving you the this simple algebra. So, you can try, so that really you learn. Okay. So, once we have these coefficients, we have the stream function given by this. So, you can see the far field structure is visible. Far field is u by 2 r square sin square theta. So, that is why we have taken the corresponding functional form as a function of r sin square theta, and we got some 2 additional things. So, what are these additional terms? Okay. So, you have a sphere and you have uniform velocity. What will happen? A streamline coming close to the particle realizes that there is an obstruction. So, it gets deviated. Okay. So, we have a symmetry. So, there we have such symmetric approach streamlines. Now, what we have computed is far field uniform plus disturbance due to the sphere. So, that is what we have computed, and what are they? So, this is the contribution 1 and contribution 2 due to the disturbance. The corresponding velocities can be nicely represented. So, this is in vector notation. If you see in component form or vector notation, this is simply u k, or in component form it is u along k direction, and these are the disturbances. Okay. Now, these disturbances can be represented. Okay. So, this is uniform flow as I explained. Then second term corresponds to a doublet, and third term corresponds to a Stokes let, right. So, you will be confused what are these Stokelet and doublet. So, these are called singular solutions of Stokes equation, and we discuss more details in coming lectures, but for now I will just mention briefly and you assume that, and in details we will learn little later. So, what do you mean by singular solution? You take homogeneous Stokes equation, whatever solutions one can get, they are regular solutions, but instead of homogeneous you take right hand side a point force, that is like a source or a sink. So, then if you solve the corresponding equation, whatever we get, they are the singular solutions, that means they are due to a source or a singularity. So, if you take at some point r equals to some a, okay, a singularity, and solve the Stokes equations, the corresponding solution is Stokelet, and higher order singularities are also can be classified. So, we discuss in coming lecture. So, this is a Stokelet and this is a doublet. Okay. So, for the time being this much information is enough. So, we have obtained the corresponding velocity components. Now, what is the next job is, you have a sphere. So, flow is coming from far field and it gets disturbed. So, in many of the physical problems, very important physical quantity of interest, in particular flow past particles, is the corresponding drag. Okay. So, that will give a lot of physics. So, the next task for us is to compute the drag force acting on the sphere. Okay. So, in order to do that, so we need the pressure. Okay. So, pressure is found by integrating the momentum equations. Again this Laplacian over these two components, they bring in a lot of algebra, but one can handle, it is not very difficult. So, how do we integrate the pressure? We know now the velocities. So, we substitute and then integrate this, then you will get a function of theta, and then use this and determine the function of theta. One can determine the pressure up to a constant. So, that constant is P infinity. Okay. So, P is given by this, comes this side P infinity minus this. Okay. So, why we are interested in pressure? Because in order to compute the normal stress, we require pressure, and then to compute the drag forces, we require the normal stress. Okay. So, therefore, what I give a caution is, the velocity components that we have obtained, they should be used here and integrated for pressure. Okay. So, this again could be a nice exercise. So, please try. Now, one can compute the maximum pressure, okay, which occurs at the forward stagnation point theta equals to pi, while the minimum occurs at the rear. So, what do you mean by these stagnation points? I mentioned this is a streamline, it will realize the deflection presence of the particle and gets deflected, but if you take this streamline, so which will hit the particle due to the symmetry, and this is called the dividing streamline. Okay. So, it divides. So, that means the surface itself is a streamline, but however, if one can measure the velocities they will be 0 here. So, these points are called stagnation points. Okay. So, this point and this point. So, stagnation point means no flow is taking place, velocity is 0, right. So, correspondingly at theta equals to pi, the maximum occurs, and then minimum occurs at the rear stagnation point at theta equal to 0. So, that means we are talking about this and this, theta equals to 0, theta equals to pi. Okay. So, this is a very useful insight. So, now we proceed to compute the drag. Okay. So, again let us recall the geometry. So, we have a uniform flow along z axis, then we have computed the difference, then correspondingly pressure is obtained, and then we got the corresponding stress components. Once you have pressure and velocity, one can compute the stress components. Okay. So, we would like to use these stress components and compute the drag force. Now, what is the definition? So, definition is force per unit area of the spherical surface in the z direction, that is force per unit area of the spherical surface in the z direction, that will be the drag in the z direction. So, why? Because we have u equals u k. So, therefore, it exerts force, this is constant. So, due to this the uniform flow exerts drag force, okay, in the z direction. That means, if the flow is in this direction, so corresponding opposite direction we get the reaction. Okay. So, that we are going to compute. So, it is given by the normal stress multiplied by cos theta minus the corresponding shear stress multiplied by sin theta. So, this is again a exercise. The stress tensor can be resolved in terms of 3 directions r theta phi. So, since here we are interested in z direction, so we are indicating this along z direction, Cartesian notation. So, we are getting this. So, now normal stress is given by this, okay, and then the shear stress is given by this. So, this just indication to know that this is along z direction. So, normal stress and shear stress, we have all the ingredients available. So, we can compute f r z at r equals to a. Okay. So, normal stress and then shear stress combination by virtue of the z direction, we are getting this cos theta and sin theta, and we can compute. So, f r z in detailed. So, again this is not expression looking very complicated, but it is very straightforward. We have all the ingredients and simply substitute and use some partial differentiation to get this. Okay. Now, how do we get the total force? By integrating. So, this f r z that we have computed, that is the force along z direction, then we are integrating with the corresponding surface element. Okay. So, that is what we are doing. So, surface element for the sphere is r square sin theta d theta d phi, and since we are on the surface of the sphere, so r is a, and these are due to axisymmetry, this is independent of phi. So, I have pulled r square as a square, and phi is coming to be variations of phi is 2 pi. So, we have this, and this can be integrated. But before we do that, so we can split this by substituting f r z. One can split this, and there is a reason for splitting this. Okay. What did we do? See what we have this f r z, and some part this is coming due to the pressure, and this is due to the viscous force. So, correspondingly what we have done, we have decomposed part due to pressure and part due to the viscous force. Okay. Then you will realize total Stokes drag, this is called Stokes drag, is 6 pi mu u a, but portion is coming due to the pressure and portion is coming due to the viscous force. So, to be more precise, we have the Stokes drag like this. So, 1/3 is due to the pressure forces and 2/3 is due to the viscous force. So, this is a very useful relation. So, for interpreting various physical quantities, this will be helping us a lot. Okay. So, this is the drag force. Now, how do we compute the drag force? Okay. We have used, I promised you getting the equation in terms of stream function. Yeah. So, if you look at it, so one approach is consider the momentum in component form, then eliminate the pressure, then substitute, the velocity in terms of stream function. Okay. But this looks slightly involved. So, let us see in brief. Okay. I may not be able to give you full details, but in brief let us see an alternative approach, okay, using completely vector notations. The idea is reducing Stokes equations in terms of vector notation. Okay. So, this is a vector identity curl vector equals to grad divergence minus del square, but for Stokes equation we have divergence q is 0. Therefore, from these two, since this is 0, del square q is negative of this, and this is a vorticity vector. This is a vorticity vector. So, Stokes equation reduces to now del square q is now this. Therefore, Stokes equation reduces to this, okay, because it is nothing but minus grad p plus mu del square q, right. Now, taking curl of the above equation, we get curl vorticity is 0. That means, this is the modified Stokes equation in terms of vorticity, right. One can represent velocity in terms of stream function using this. This is nothing but u r, whatever definition u r u theta we have, exactly we get this. Okay. We will see if we expand what you get, but for the timing you assume that q can be written like this, and therefore, vorticity simple curl if you take, we get already you are seeing whatever E 2 we have, that capital E square for the Stokes operator, we are getting that. But what is the Stokes equation? It is 2 times curl. So, therefore, we take another curl and equate to 0, exactly we are getting this is E square and square of that. So, E for psi is 0. Okay. So, this is a very simple approach via vector equation, okay, and this is anybody can see you are exactly getting the stream function. Okay. So, these are some simple things I thought in compact form we will show you, but you can verify. Okay. So, similarly, curl q also one can calculate, and you are almost getting E square. Okay. So, this will give you Stokes flow past a sphere. So, what we have done is we have integrated the Stokes equations and obtained one scalar equation in terms of stream function. Then as an application, Stokes flow past a sphere has been discussed, and for physical insights we have computed the Stokes drag, that is force acting on the surface of the sphere. Thank you.